In this question, we've been told that a uniform rod AB has length 14 meters and weight 53 newtons. The rod rests in equilibrium in a horizontal position, smoothly supported at points C and D, and we're given the distances from A to C and A to D. A particle of weight W is attached to the rod at point E, where AE is going to be represented by X. We have enough information to start producing a sketch to model the situation. So here's our rod. We know that it's uniform, so we can model our weight right at the center, and that's going to be 53 newtons. The rod is called AB, so we label the two ends A and B. The first support is C, which is 2 meters away from A. So I can put the support and label 2. The second support is over here. This is D. It's 9 meters away from A. If it's 9 meters away from A, that means it's 5 meters away from B. So we can simply add in a 5. We're told that the reaction force at C is going to be 4 times the magnitude of the reaction force at D. So I can label these as R at D and 4R, 4 times the size, 4 times as big over here at C. Additionally, we're told that there's a weight W that has been added to the rod at point E. We do not know exactly where to place point E, but because the reaction force at C is larger, I'm going to place it in close proximity to C. So W goes here, and we just need to decide how to label the last few sections. I know that this is a uniform rod, so the distance from A to the center, from A to the weight 53 newtons, is going to be 7. So the space between C and the center is going to be 5. The unknown distance from C to W, I'm going to call that Y, which means this is 5 minus Y. Together they make 5, Y and 5 minus Y. Meaning from the center to point D is 2 meters. Now I've labeled this exactly how I want. However, the question has told us that AE is going to be represented by X. On my diagram, AE is 2 plus Y. So at some point, I'm going to want to substitute X back into my expression. So if I have any Y terms, I can substitute them for X minus 2. I could have labeled this as X minus 2 in the first instance, but both ways will get us to the correct result. Part A of the question asks us to show that W equals 190.8 over 3.4 minus X. Now that we have a good diagram, let's see if we can get that expression for ourselves. We'll start with the strategies we usually use when working with equilibrium. Equilibrium indicates that the forces in opposite directions are going to be equal to each other. So if we look vertically and we resolve vertically, the forces up will equal the forces down. 4R plus R equals W plus 53. 5R, W plus 53, and R is the W plus 53 over 5. What else can we do? We can take some moments. I'm going to choose to take moments from C. Taking moments from the point C means I have 3 forces to consider: W, 53, and R. W and 53 are going to produce clockwise moments, while R is going to contribute to an anti-clockwise moment. We're going to use the perpendicular distance multiplied by the force. So the distance from C to W is Y. Y times W is the moment. The distance from C to 53 is 5. 5 times 53, and they are going to equal 7 times R. On the next line, I'm going to substitute. I'm going to substitute in the X expression in place of Y, and I'm going to substitute in the fraction that we found for R, the fraction for the reaction force. Okay, just expand the brackets. Let's see the actual terms that we're working with. I have 3 terms with a W in them. I'm going to get them all onto one side of the equals, and all the constants onto the left-hand side. From here, I can start to simplify. 265 minus 74.2 is 190.8. So that makes me feel that we're on track. On the right hand side, I'll factorize out the w, and I'm left with 3.4 minus x. Once again, that appears in the final expression. One step of rearranging, and we have got the final expression we were asked to produce. So we have shown that w equals 190.8 over 3.4 minus x. In part B, we're asked to deduce the range of possible values of x. The question does start with hence. This always tells us we should be using the answer we've just produced to help us with this part of the question. Well, looking at this expression, there are some limitations. We have a fraction. We know that we never want the denominator of a fraction to equal 0. Otherwise, that expression is undefined. This denominator would equal 0 if x was 3.4. So we want to make sure that x stays below 3.4 so it never produces an undefined weight. Additionally, we don't want x to be bigger than 3.4 because then that would give us a negative weight. 3.4 subtract 10 would give us negative 6.6. And that would be a negative weight, which wouldn't make sense in our context. So we know that x has to be smaller than 3.4 to ensure that w is a positive value. Similarly, x itself needs to be a positive value. X represents a length. A length in this instance cannot be negative because this is the distance from A to a specific point. A negative value would place the weight to the left of A, which means it would not actually be on the rod at all. So that wouldn't make sense for the context of our problem, for the model that we've produced. So x must be positive, meaning it's larger than 0, and w must be positive, meaning that x is smaller than 3.4. Those two things are the limits that we have on x. So the range of possible values of x are in between 0 and 3.4, but not including either of those two. So 2 elements of rationale to help us deduce our value for x.